Okay, so a catalyst is the final way that we need to study to increase the rate of reaction. And it's like the end of 6.5. So this isn't its own section. You're going to see why I waited for the end. Or if you have the note printed off, you can see it on there. We're going to look at what happens with a catalyst in terms of the two diagrams that we have looked at in this unit. So potential energy diagrams revisited and Maxwell-Boltzmann distribution. Okay? So a catalyst increases the rate of reaction without being used up. And why is it important that it is not used up? That makes it not an overall reactant or product. Okay? Economically, we use catalysts all the time. Catalytic converter in your car makes, even though the combustion reactions inside our car is not great, it would be even worse if we did not have catalytic converters. Our bodies use enzymes. We could not survive and process food into energy fast enough, that kind of thing, okay? So how is it different from a reaction intermediate, which we also wrote in this morning's note, not an overall reactant and product? So in this case, a catalyst, we are going to say that it's used up, but then it gets regenerated. So highlight that. So the way that we are going to figure out how that works in a mechanism, it'll be a reactant in one step, and then a product in a later step. It's still an intermediate substance, so it's still difficult to say exactly what's going on. So it is classified as a theory based, or best guess based on the observations we have, are that it lowers the activation energy, which makes sense. If you lower the activation energy, then the reaction will be faster because now you've lowered the barrier. More particles will have the minimum. So we can look at activation energy, so the potential energy diagram, and logically, if it lowers the activation energy, which is potential, then it also will lower threshold, which is the minimum kinetic. So we can influence or affect the two types of diagrams we did. So if you have the note printed off, you can see them both there, okay? For good reason. All right, so it lowers the activation energy. So a larger fraction, which is just more of them, will have enough, are considered to have enough energy to react. We believe that it stabilizes the transition state, especially for heterogeneous catalysts like the catalytic converter. It's metal. It provides a surface for the gases to bond to and to help stabilize them to make the reaction happen faster. Or it could also lower the activation energy by providing an alternate mechanism. And what's a mechanism? You have more than one step, okay? So that's a possibility. So then you're getting, if you have a new mechanism, you could have new reaction intermediates that are maybe more reactive, something like that. So again, we're going to, because it is a theory, we are just going to deal with generalities, okay? So we'll talk about the potential energy diagram first. So if you want, I can't photocopy, or sometimes it doesn't print in color. What I would do is, if you have like some way to make it um, stand out a bit, so the catalyzed pathway is the two hump one. So this potential energy diagram is showing a catalyst, and how do I know that? Because it's providing an alternate mechanism. How do I know that it's providing an alternate mechanism? There's two peaks. So in this representation, how many steps would there be? Two, okay? So we can write that down. It doesn't have to be at the top here, you can write it anywhere. So it doesn't really say much of anything. It doesn't show um, the reaction intermediates or anything like that. Again, it doesn't even, it just says reactants and products. It really is just a generality, but when you have more than one peak, then that means you have more than one step. So a couple other things to notice. So we want the reaction to go faster, but we don't want to get less energy out of it. So it says here that the delta H is the same. How did I know that? Because the reactants and the products, the overall, are still in the same spot. So the catalyzed reaction starts and ends in the same spot. Okay, so here reactants, here products, for both catalyzed and uncatalyzed, are in the same position. We have drawn two peaks to take into account the idea that it provides an alternate mechanism, but also, not only do you want an alternate mechanism, overall, these peaks are lower than this big one. So that means then that overall, the activation energy is also lower, which is what we want, okay? I just realized this isn't printed. Okay, so that is potential energy. If you want to add that in, I might have cut it off. So the peaks are lower and there's more than one. So if you're asked to draw one in, you can really do whatever you want. Just make sure it starts and ends in the same spot, and then you could draw a million little peaks if you wanted to, okay? They just have to be lower. Yeah, potential. I realize it just says energy. Oh, if you want to add that in. I must have cut it off first. Or you're right, Tracy. I think this is good. Okay, so then the next diagram, I highlighted potential. Please, please, because it's so annoying because they almost look identical. This Maxwell Boltzmann is kinetic energy. Oh, and it doesn't say that on here. My goodness. So the catalysts are the only factor that can change or lower the minimum energy required. So yesterday we did concentration and surface area, which can change the frequency of collisions. We did temperature, which can change how often and how much energy they have. And then catalyst lowers the barrier. So if you go back to our really unfortunate analogy, if this is the student and the school has a high entrance average, very few of them get in, and then for whatever reason they decide to lower it, more students can get in, okay? So one more time, it is very frustrating. This almost looks like a potential energy diagram. So when I ask students to add a catalyst, then you have to remember to lower the threshold energy. And it's a very common mistake to do something like this. That's not what goes on this picture, right? So what you need to do is think of what's happening in this graph. It's like a normal X and Y. This is 0. So if you have, this says the original. Oh wait, you guys have that on there? Perfect. Let me write it down. because let's call it something else, okay? So we'll call this the uncatalyzed threshold, or original maybe. You like that better? Never mind, I can't get it. If you want, make up a number. So we can call this, let's say, 75 kilojoules. So at 75 kilojoules, that's the threshold barrier. This green spot is how many particles are past the threshold reacting. If I asked you to lower the threshold by adding a catalyst, that means that you need to get closer to zero. Okay, so this is like a kind of like a normal style with zero. This is the origin in the corner here. So this is a lower threshold. So if that's 75, let's make that up. We'll call this 50. Okay, so at a lower energy, more particles will react. So it does say that here. It does say originally, the number of particles represented by this little shaded area under the curve have enough energy to react. And then when you lower the threshold, now all these do as well. When you have more particles colliding effectively, reaction will be faster. Okay? So these questions, I forget if it's one or two, ask you about a Maxwell-Boltzmann distribution. So I highly recommend doing that question so that you can see what's going to happen when you manipulate that kind of diagram. Because we haven't dealt with this before, sometimes it can be tricky to sort of separate in your brain what's potential energy and what is kinetic. And these questions are listed on the worksheet and the solution is on the back, okay? And on D2L as well, actually. So then another type of question is taking a look at a mechanism and deciding which substance is the catalyst. Okay, so given the overall reaction and the proposed mechanism below, distinguish between the catalyst and the reaction intermediate. So I'm going to kind of make like 2 columns. Oh yeah, you did lots of room. Okay. Leave a little space at the bottom. So reaction intermediate versus catalyst. So the very first line in both the definitions talks about not an overall reactant or product. So both of them you would have canceled out. Okay, so that helps us distinguish between, what is an intermediary, but not between both of these. So let's cancel stuff out. AX is a product and a reactant. It cancels out. And then X this is a very simple example, okay? So the reaction intermediate, there's only one of them. You could have more than one. A catalyst, you can only have one. So that's another distinguishing feature. But let's look at the definition first. So reaction intermediate, we defined it as something that was produced in one step and consumed later. And a catalyst, we said, was consumed and regenerated or reproduced. If you don't like the word regenerated, that's fine. So I am not going to look at A and B and AB because they were not crossed out. You can see them if you're given an overall reaction, then they're in the overall. That's another clue as well. We don't care about those. We want to look at the difference between AX and X. Which one is produced in one step and consumed in a later step versus being consumed or being a reactant in one step and then being a product in another step. So it doesn't really matter what order you do it in. X is first. So here it's being used up, but then down here it gets reproduced. So the catalyst gets regenerated. Why is that important? Because you want it to be able to be reused. Imagine every combustion reaction occurring in your car. If you then had to go get a new catalytic converter, that would be insane, right? So we want the catalyst to be regenerated. So I'm going to use red to help emphasize, okay? So X is a reactant in step 1, and then it's reproduced in step 2. Versus AX, which is a product in step 1, but then it's consumed or it's a reactant in step 2. There's another thing that's not really demonstrated here because it's so simple, this mechanism, but you can have more than one reaction intermediate, but you can only have one catalyst. That can be another clue of that you've done it right, I guess. And then one more thing too, so if you've ever looked at a reaction and there's something written over top of the arrow, so trying to indicate it's not an overall product or reactant, then that's how we actually include catalyst in the representation of the reaction. You might even see sometimes like a little triangle, which means heat is required. You might see H nu, which means like UV light is required. Generally speaking, when there's a very specific type of condition required for a reaction to go, then writing it over the arrow can sometimes be used as the notation. Okay, and then the rest of the note is basically just definitions. Okay, so there are two very broad categories of catalysts, homogeneous and heterogeneous, which are exactly the same as the terms you learned in grade 9. Okay, so homogeneous is the same phase or the same state. So here, oops, I think the arrow's okay on your paper, right? So you have aqueous reactant, aqueous product, and aqueous zinc chloride is the catalyst. So if you want, you could even write it over top of your arrow. All of them are in the same phase or state. The reaction takes place in an aqueous solution, and the catalyst is soluble in water. So zinc chloride is considered to be a homogeneous catalyst because it's all aqueous, or could be all gases. Probably not all solids. Solids generally are very boring in reactions. It's more likely that a solid will be a heterogeneous catalyst, like the example we're going to talk about in a second. Okay, so then heterogeneous in a different phase. I wanted to try to keep this all on one page here, so it is kind of small, so if you'd rather look at your notes, it's exactly what's on there, okay? So, different phase or state. Just like with surface area, which was solid gas, or aqueous and solid, that's a really common thing here. Like the catalytic converter in your car, usually it's rhodium or palladium, a very precious metal. That's why they're often stolen from cars, because it is pretty expensive. There are lots of examples of solid catalysts that are metals. So for example, this reaction is called hydrogenation. So, and you know, hydrogenation is kind of a bad word, especially in nutrition. You're changing unsaturated fats into saturated fats by adding hydrogen, which is bad, you know, supposed to be bad for you and your arteries. Okay? So without a catalyst, this reaction is very slow. So you can use a metal, and so again, sometimes written over top of the arrow, palladium or platinum catalyzes the reaction. And the way that this works, this specific example, this is ethylene, sorry, and hydrogen are actually more attracted to the metal than they are to each other. So it's like the metal provides a surface for them to meet. And then once they get there, then it's like, okay, now we'll react. Whereas if they're just hanging around in a reaction vessel, then they're not as likely to get together because they're more attracted to the metal, then that's where they're going to meet. So the ethylene hydrogen molecules form bonds with the metal surface. So they're attracted to the metal. This weakens the, they come there, they are going to react with each other. Then the hydrogen atoms break, molecule atoms break, bonds break, and it provides a surface for the reaction to occur. To be honest, I probably wouldn't ask you specific details about this if you like to make your own study notes, but this is just a good example of how this works. The metal is a solid, the gas is attracted to it, so they are in different phases or different states. The reactants are gases and the catalyst is a solid. And don't push out of your brain things you already know. You would know that metals are solids, right? And then the last teeny tiny definition, an inhibitor prevents the reaction from occurring. It's like the opposite of a catalyst. So preservatives would be the opposite of a catalyst. They are molecules that prevent reactions from occurring in food, in medicine, even something like decreasing the temperature, putting in the fridge, putting it in the freezer. Why do we do that? To prevent decomposition reactions from occurring and spoiling, which some cases, some types of spoiling are caused by molecules. In fact, ethylene is the molecule that causes spoiling in fruit. And it's even worse that fruit that is already spoiled releases more ethylene to spoil the fruit next to it. It's like a chain reaction. So inhibitor reduces the reaction rate. So this is really the opposite of a catalyst.